cannot hear me. Can you hear me?
It's recording in the cloud now.
Okay, yeah. So as long as you can hear me, I will turn off my mic. Thank you.
Oh. Okay, sorry for that. So let's start now. Let me share the screen for a moment. So I was saying thank you everyone for being here in our monthly seminar for this Latin American gravitational wave community. Let's start with our announcements. So we just want to recall to our community's members the different meetings, conferences that are going to happen in the next weeks, months, or even in the next year. So let me start remind you about this third generation gravitational waves detector debut from Latin America, which is going to happen in less than a month, or maybe a little bit more than a month, in Sao Paulo, Brazil. So people is invited to check the website here. So our second event is this one, the fourth School of Gravitational Waves in Astrophysics, which is going to happen in Chile. It is going to be early next year. There is no website yet, but we will announce the website as soon as we have it. There is also a public call for research projects for this Latin American and Caribbean Cooperation Program in Science, Technology, and Innovation. So you are more than welcome to visit the webpage. There are several topics there: health, sustainability, and other topics that might be interested for some of you. So also, you are invited to check this North American Einstein Toolkit workshop and school, which is very important for people working in numerical relativity and related fields. And finally, I'm going to give a couple of minutes to
Yeah, it seems Mauricio is having
talk
problems
about
with
this
the
Latin
Wi-Fi.
American conference, right?
Yes, can I just share the screen? Yes. Okay, I am assuming you are watching my screen now, and then I'm just going to take about 2 minutes just to announce that we will be organizing the second Latin American Conference on Gravitational Waves. As you know, the first one was from the initiative from our colleagues from Brazil. So in the meeting in San Jose dos Campos, they encouraged us to try to organize a meeting in Mexico. So we took the initiative, and then, well, we talked with lots of people, and we will be organizing this. This is going to be by the end of September next year. So we have lots of time to organize it. And it's going to take place in a very important institution in a place called Puebla, near to Mexico City. So the acronym is INAOE, which in English, it stands for National Institute of Astrophysics, Optics, and Electronics, which are basically 3 of the basic sciences that are required for detection of gravitational waves. So it should be a very good place to promote the science of gravitational waves. And they also work a lot on computer science. And this event is also going to be supported by the local university from the state of Puebla, which in English is Emeritus Autonomous University of Puebla. And as was the case for the meeting in Brazil, the aim is to promote the gravitational wave science in Latin America. And of course, in particular, we want to promote this type of science in Mexico as well. Mexico has a very strong tradition, very old and strong tradition in astronomy. However, the people who are actually doing research in gravitational waves is really very small. So we want to change that. So this institution is in a place called Tonancintla, which is conveniently located close to Mexico City. That is good for transportation, but it is also very good because in Mexico City, there's lots of people who could be potentially interested in doing research in gravitational waves. So it is a very good place for them to easily go. And then I just prepared another slide just for you to know this institution in which this conference is going to take place. This institution is famous, among other things, for hosting two very important astronomical observatories. So one of them, which is shown on the upper left of the screen, is called the Large Millimeter Telescope, Alfonso Serrano. Alfonso Serrano is the guy who actually promoted the construction of this telescope. So this is the world's largest single dish steerable millimeter wavelength telescope, which is basically 50 meters. So it's really, really very long. And it makes observation in wavelengths between 850 micrometers and 4 millimeters. And it is located at 4,600 meters above sea level in the Sierra Nevada. And it is also well known for participating in the collaboration Event Horizon Telescope. And as you know, they took this picture here from the accretion disk of the black hole in the galaxy M87. And this project is a collaboration between INAOE and the University of Massachusetts Amherst. And then another very important observatory that they host is the High Altitude Water Cherenkov, which its acronym is HAWK, which is a very convenient acronym as well. And it is a gamma ray observatory, which is located very close to the Large Millimeter Telescope. So it comprises 900 water tanks, 5 meters in diameter, covering an area of 20,000 meters square. And that collaboration is a collaboration of 30 institutions worldwide. So I think we are quite happy that they are interested in hosting this conference. So we are looking forward to see you next year in Tonancintla. This is all.
Thank you, Fabian. Thank you. So as part of our announcements, if any one of you guys has any announcement, any comment, any advertising, so this is the moment a good moment to do it. Okay, perfect. We have Alexander there. So Alexander, go ahead.
Thank you. Hi, everyone. Very interesting meeting. Fabian, you know, if you have a financial support or something like that?
Sorry, can you say that again, please?
You can hear me?
Yes, we can hear you very well.
Okay.
So, but I was not able to understand.
You know, if you have a financial support.
Oh, okay, yes.
It's clear.
We're
the
aiming
question?
to get money. We're aiming to get money from the government. You know, the well, it was formerly called CONACYT.
Yes.
So,
participation.
I am not able to
only if you know.
Alexander.
So you are breaking.
No, only if you know. Excuse me, something is wrong.
Yeah, you can.
Yeah, so
it in the chat.
We found a call from the Mexican government to be able to get money for international conferences. So we will be asking for money. So we will be inviting people. At least that's the aim. So we will apply for the money until next year. So we will be telling you more about this.
Okay, thanks.
Yeah.
Thank you, Alexander. So anyone else has any announcement, comment, advertising? This is a good moment. If not, at the end, we can also spend a couple of minutes for that too. Just wait 4 seconds. 2. Okay. So let's move now to the seminar. So today we have two great speakers. They are Sergio and Antonio from University of Antioquia in Colombia. So we're going to start with Sergio with the presentation model agnostic constraints of gravitational-electromagnetic luminosity distance ratio. Let me give a short introduction about Sergio. Sergio is assistant professor at the Institute of Physics in Universidad de Antioquia in Medellin, Colombia. His research focused on gravitational wave cosmology, particularly in the luminosity distance and modeled independent tests of gravity. Importantly, Sergio is part of the LIGO Virgo Cagra collaboration in the CBC cosmology group. And Sergio is PhD in physics from University of Antioquia in Medellin. So, Sergio, thank you for being here for this presentation for today. The space is yours now.
Hello, thank you. Okay, good day to everyone. I'm going to share my screen in a second. And okay, let me start something here. Okay, can you see my slides, right? Great, thank you.
Perfectly.
Okay, so today I'm going to talk about a new method that we have been working on during the recent times, about constraints which allow us to constrain the gravitational electromagnetic luminosity distance ratio. This is a work that I've been doing in collaboration with Professor Antonio Romano and Professor Jonathan Greer. And you can find here the link to the e-print of the paper in which I based this presentation today. Okay. So I give you here a very brief outline of the talk I'm going to do today, to give today. And I'm going to start talking about what are gravitational wave standard sirens, which are a key ingredient of gravitational wave cosmology. Then I'm going to enter into the details of bright and dark sirens. Probably many of you already know many of these aspects of gravitational waves. And then I'm going to mention briefly two of the main pipelines that are used by the LBK collaboration to do cosmological analysis based on gravitational wave data. And then I'm going to focus on the gravitational electromagnetic luminosity distance ratio, which is a key quantity that we are studying. And then I'm going to discuss briefly what is the non-parametric method that we have developed. And finally, I will move to the constraints that we obtain with gravitational wave events from the third transient catalog. Well, from the BBHs coming from this catalog. So basically, to start with the gravitational waves as a standard sirens, the key idea here is that the amplitude of the strength of gravitational wave is inversely proportional to the gravitational distance to the source. And in the case of general relativity, I will mention this again later, the gravitational wave luminosity distance and the electromagnetic distance are the same quantity as in general. So this is the basis of the idea to use gravitational waves as new sirens, new objects to calibrate the expansion of the universe. So basically, the only issue here with standard sirens is how do we get the redshift of the source, because there is some degeneracy that I will mention again later as well between some source parameters, for example, the masses and the frequencies, and the frequency with the redshift of the source. So basically, this makes impossible to get the redshift from the gravitational wave strain signal. So we can only obtain the distance. So there are different methods in which we can do cosmology, and these rely on different estimations or measurements of the redshift of the gravitational wave sources. And one of the most direct way to do it is with bright sirens. In this case, together with the gravitational wave, there is a electromagnetic observation that, in principle, are considered to be from the same source. So we have one event so far that we consider a bright siren, which is GW-17 and this event, there were many observations after the gravitational wave observation in the electromagnetic spectrum. The first one coming in the gamma spectrum of the electromagnetic spectrum, and basically subsequent observations in other wavelengths allowed to measure or estimate the redshift of this merger of these two BNSs. And in this case, there was this association between the electromagnetic signals and the gravitational wave signals, so that this allowed to a direct estimation of the Hubble constant, for example, for the first time using bright sirens. There are statistical methods that allow to estimate cosmological parameters using dark sirens, which are these gravitational wave events that does not have a confident electromagnetic association. And in this case, we have, for example, the spectral siren method, which is basically a method in which we assume some model or distribution for the masses, source frame masses of the event, and using this relation between detector frame mass and source frame mass given by the redshift of the source, using features in this distribution of the mass spectrum, we can infer cosmological parameters using some hierarchical Bayesian approaches right now. So basically, the key ingredient in this method is this relation between detector and source frame mass, and basically adopting some specific model or distribution for the population of the compact objects. And this method is statistical in the sense that this works better as we increase the number of detections. So this is different to the bright siren case, for example, in which with a single event we can get a very good posterior or very good estimate for the Hubble constant, for example. There is other dark siren methods which relies on the use of the galaxy catalog of galaxy catalog information. So in this case, this is another statistical method in which there is a large sample of or a catalog with a large number of galaxies, and one example is, for example, this Glade catalog. In this case, we use the redshift information coming from the galaxies in the catalog, and using the sky localization of the gravitational wave events coming from the sky area and the distance, we can infer where, with certain probability, where this event came from, and look at what galaxies are located along this region of space-time, and then of space, and then from this and the galaxies located within this volume, we use the redshift information of those galaxies in order to infer cosmological parameters. And in this case, this also relies in assuming some population model. You can in the most recent cases, we can actually jointly constrain the population parameters of the mass distribution with the cosmological parameters such as H0. using also or including also this galaxy catalog information. And this method is also less informative than the bright siren one, but when the information is combined, the information from multiple events is combined, then the uncertainty can be reduced and we can get good estimates using this method. Okay, so I'm going to move now to an example of basically how what was the first estimation of the Hubble constant with the bright siren. So this is a result that was obtained by the LIGO-Virgo collaboration in 2017, quite famous, in which they basically obtained this posterior for the Hubble constant using the so far only bright siren GW-17 and the idea is very simple. We know from the FRW universe that there is a relation between the Hubble parameter and the luminosity distance, and basically combining the measurement of the distance from the gravitational wave and the redshift from the electromagnetic waves, it is possible to estimate the Hubble constant in this case. And this is the constraint that was obtained for that event. This is an important discovery because gravitational wave sirens, standard sirens, would allow us to shed some light on the Hubble tension, and this would be better as we have more events and with better precision in their detection. Okay, now I'm going to quickly mention the two pipelines that are used to estimate these parameters by the LIGO-Virgo collaboration. So basically, currently, these are GW-Cosmo and ICARO-GW. And in the beginning, GW-Cosmo, for example, was developed to apply the galaxy catalog method, assuming some fixed population for the source frame masses. And ICARO-GW was developed with the goal to apply the spectral siren method. So at the beginning, the ICARO-GW didn't include or didn't use, it was not designed to use the galaxy catalog information. But currently, both pipelines have been updated or upgraded to both infer jointly the population parameters and cosmological parameters, and also to make use of galaxy catalog information in a slightly different ways, but in principle in equivalent ways, leading to equivalent posteriors of the Hubble constant. And in this case, I'm showing you the posterior of the Hubble constant that was obtained with the upgrades that allow for both codes to do this joint estimation. So in these cases, they are using galaxy catalog information with ICARO-GW in this case to obtain these constraints on the Hubble constant with GW-TC2 events. And in this case, this is the result of GW-Cosmo after obtaining the constraint on the Hubble constant by marginalizing over the source parameters using GW-TC3 data. So now I'm going to move on the luminosity, gravitational wave and electromagnetic wave luminosity distance ratio. So as I mentioned before, in general relativity, gravitational waves propagates in a way that the gravitational wave and electromagnetic wave luminosity distance are equal. So as mentioned in this equation here, and in a flat universe, we have that the electromagnetic luminosity distance, this is the general relation. At least in a lambda CDM universe with some radiation component, okay? But in modified gravity theories, the propagation of gravitational waves is different from that of general relativity, and this could give rise to a modification of the above relation. So basically, we could have a different relation between the gravitational wave luminosity distance and the electromagnetic luminosity distance. And it is useful to account for this difference to introduce this distance ratio quantity, which is defined as the ratio between the gravitational and electromagnetic luminosity distances. So the idea is that the same method that allows to constrain cosmology or cosmological parameters, assuming general relativity with gravitational wave standard science, also allow us to put constraints on this quantity if we allow for the two luminosity distance to be different within the pipelines that we are using. So in GW-Cosmo and ICARO-GW, there are some parametric forms of this distance ratio. For example, this is a very well-known one, which is known as the Chi0n parametrization, motivated by some modified gravity theories. And there are other parametrizations which are motivated, for example, by this Ordensky class theory and the extra dimensions parametrization. And so the idea here for us was to, well, there are these parametric methods to constrain the distance ratio using this gravitational wave standard science, but we would like to try to develop a non-parametric distance method to estimate the distance ratio. And basically, we have implemented it in GW-Cosmos so far, but this method could be implemented in ICARO-GW as well. So since this is implemented in GW-Cosmos, I'm going to mention basically what are the conditions within this pipeline, but they are very similar in ICARO-GW. So the idea with GW-Cosmos, as I have mentioned before, but here's the key equation that allows us to do it, is to compute the posterior distribution of some set of parameters, cosmological parameters such as the Hubble constant, source frame population parameters, and in the case of the distance ratio, parameters related to this quantity, applying this hierarchical Bayesian analysis according to this equation. So here, the quantity theta represents the source, the individual source parameters of each gravitational wave event considered in the analysis. So this is for a number of detections. And basically, in this case, we need to marginalize over the source parameters to obtain the population and cosmological, let's say now, hyperparameters here. So there is also a prior on the hyperparameters that need to be used, but in general, this is the way that we can obtain the posteriors using this likelihood. And in the case of these joint estimates of cosmological and population parameters, and in general, there is this key relationship that I mentioned before between the source frame mass here and the detector frame mass. And this is mediated by the redshift, and the redshift for the events is not known. So this has to be computed based on the distance of each event. And in the case of the gravitational wave observations, we have posteriors of the distance. So we need to compute the redshift, like a posterior of the redshift based on this posterior of the distance. So this is a key aspect of the method that we have to bear in mind, that we need this relationship between redshift and distance. Like basically, we need to be able to compute the redshift based on a given distance, given gravitational wave distance. This is not only important because of the detections, because of the events observed, but also because of the injections that are used to compute the selection effects, which are basically here in this denominator of this likelihood. Okay, so for the non-parametric gravitational wave and electromagnetic distance ratio, we are using a piecewise cubic Hermitian interpolating polynomial chip to do this reconstruction. And we, in the case of GW-Cosmo, need that this basically we are constructing this polynomial in such a way that we have the luminosity distance, the gravitational wave distance as a function of the redshift. But as I mentioned before, we also need the redshift as a function of the distance, so this has to be invertible. And basically, to make this invertible, the most simple way to do it that we follow first was to use a monotonic function for the distance ratio that in the case that it was decreasing, it was not decreasing very fast, so that this is monotonic. So that's basically the idea here, because this quantity is always growing. So I will show you here some examples of how this is built. So this is built based on two parameters, which we call ρ1 and ρ2. These parameters are not exactly the values of the distance ratio, because we need to impose some constraints in order to make it monotonic, or monotonous. So in this case, what we are showing is that by varying, for example, fixing the value that is, let's say, determine the value of the distance ratio at the second node. So this is based on an interpolation on different redshift nodes. So we fix this parameter at the second node, and the first parameter is vary here, so we can see the effects when this is decreasing, and here when it is increasing, this parameter ρ1, so this one can have both negative and positive signs, and this parameter is controlling basically the shape of the distance ratio, so if whether it's decreasing or increasing, growing or not. And in the case that we fix this parameter but vary the second one, we see that how this affects the chip distance ratio here. So basically, all of them pass through the same distance ratio value as the first node, but in the second one they vary. So in this case, they vary in both cases, because the second value is affected by the first one. So I'm not going to enter into the details of the math behind this method, but these are examples of how it works, and I will just move on quickly to the constraints. So we use the for the data to constrain this, we use for the catalog of gravitational waves, we use 42 binary black holes coming from GW-TC3 with SNR greater than 11, and we use for the galaxy catalog information, we use this catalog which is Clade Plus, which is an extended galaxy catalog. We use it in the K band. And this is with a pre-computed line of sight redshift prior that was used also in the GW Cosmo paper. And then for the population model, we need to adopt a CBC merger rate evolution model. We follow the Maddow-Dickinson profile, which is given by this equation. This is the standard profile that is used for the merger rate. And in this analysis, we consider for the BBH population. Sorry, I put here an SBH, but in this analysis we are only focused on BBHs. We use the power law plus peak model, which for the primary mass distribution has this form. This is a power law and this is a Gaussian distribution. They are correctly normalized, and this is built in such a way that the distribution is also normalized. And the secondary mass distribution for the cases of the BBH is described by a truncated power law similar to this one, with a different slope and different limits in the masses. And we use these priors for the different parameters. These are the merger rate parameters. These are the mass population parameters. Yes.
If possible, 1 more minute or so.
Yeah. I will finish. Yeah, sorry. Yeah.
Thank you. Thank you. Sorry for the interruption.
Yeah, yes, it's okay. And then for the Hubble constant, we consider this prior, and this for the other for the two parameters that control the distance ratio using the chip method. In this case, we are considering only two free parameters, which is the minimum number of parameters that we can use. And in this case, the interpolation is using 4 nodes. And here I show you the constraints. This is a reduced corner plot of the constraints obtained for the merger rate parameter gamma. This is a parameter which affects basically the Maddow-Dickinson profile, and these constraints on ρ1 and ρ2. And these constraints are in agreement with general relativity, because for the method that we have developed, basically general relativity is obtained when this ρ1, this parameter, is equal to 0. So that's the limit. So in this case, we obtained an agreement with GR And in this final plot that I want to show you, this is the reconstructed posterior of the distance ratio using this method. These are the 95% and 68% confidence interval. The median is here, this line in blue, and the black line is general relativity. So as you can see, general relativity is within the confidence intervals of our reconstruction. So this is according to our results in agreement with general relativity in the current data, or well, at least GW-TC3 data. And I think I will leave it there. Thank you very much for your time and attention.
Thank you, Sergio. Fantastic presentation. So we have time for one, maybe two questions. If anyone in the audience wants to ask a question, that's great. If there is no question, maybe we can start with the next presentation, and at the end we can have a question for you too, both guys. Yeah. Okay, so let's move to our next presentation. So Antonio Nea is our next speaker. He's also a professor at the Universidad de Antioquia in Medellin, Colombia, and his presentation is...
Can you hear me? Hello?
Yes, we can hear you.
Okay, let me share. Am I sharing the full screen right now? Can you see what I'm sharing?
Yes.
Okay, so I'll try to drop this within maybe 15 minutes, so we can stay within the hour. But thank you for the very nice introduction to Sergio, so I don't have to go through all the basics of gravitational wave physics, astronomy. So the topic of my talk is how you can set some constraint on the deviation, possible deviation from general relativity or other prediction of fundamental physics using gravitational waves observation. And as Sergio was mentioning, one very important quantity is the distance ratio, and I will actually base most of my talk on that. So this is an outline of what are the things which you can actually constrain using multi-messenger astronomy observation. So you can improve, obviously, constraint on the speed of gravity, because from the time delay between the two observations, we can constrain also the relative difference between the gravitational and electromagnetic waves speed. Then we can set constraint on the effective field of dark energy. I will show you what I mean by that later. And then we can, for example, test whether or not the Planck mass is running or not, which is related to the modification of the propagation of gravitational waves on cosmological scales. And then you can actually also set constraint on the effective coupling between matter and gravity, which is responsible for structure formation. I will show you in the second part of the talk that this is possible. And then finally, we can apply this to test the consistency between gravitational waves and other probes of dark energy or modified gravity. Okay, so let me start with the discussion regarding the time delay. When we have a multi-messenger event, by definition, this is the distance which is traveled by the gravitational wave and the electromagnetic waves is the same. And this is given by this formula, which I'm showing you here, which come from the Friedman cosmological model. So the only difference between these two integrals is the speed of gravity, is the possible difference between speed of gravity and the speed of electromagnetic gravitational waves. So if you do the math, then you can find out that there is a relationship between the relative difference of the two waves and the observed time delay between them, and also the source time delay, because possibly there is a time delay at source due to some astrophysical process. And then this is also depending on the ratio. So what this formula is telling us is that once we observe the time delay between in this multi-messenger event, and then we make some astrophysical assumption for setting this number, which is the source time delay, then we can constrain the relative difference, okay? And so this has been done in the past, but you can go beyond that and assume that actually the gravitational wave distance is not constant, but it's a function of the redshift. This is actually possibly predicted by the effective theory of inflation. And so if it's a function of the redshift, it's also a function of, it's a function of time, which is the prediction of the effective theory. It will also be a function of the redshift. And in this simple case, I'm considering a possible linear dependency of the speed of gravitational wave with respect to the redshift. So this delta V1 is this linear coefficients of the dependency. And so doing a similar calculation, basically imposing by the distance traveled by the two waves is the same, then you will get this constraint of delta V1, okay? It's a slightly different formula from the other one I showed you earlier. But then again, it is depending on the time delay at the source and the observed one, okay? So if you want, you can go beyond this thing and include some other possible effects of cosmology. Basically, this formula derives under some different type of approximation. And so in this case, you will get also the dependency of this difference on the omega method, okay? So in this table, I show you what are the constraints that you can get from the observation of GW-17 OI-17 for the relative difference between the two speeds. The first column is showing you the result using gravitational wave observation and the time delay. And the second column also the redshift of the electromagnetic counterpart. So the reason why the second column has a stronger constraint is because the error on the electromagnetic redshift is actually smaller than the error on the gravitational wave distance. The gravitational wave distance is a quantity which is quite difficult to constrain because it's degenerate with other quantity like the redshift, the mass, and the inclination angle of the source. So that makes the posterior or the measurement of this quantity more uncertain than the redshift, which is instead very well constrained. Okay, so that's the power of this multi-messenger event. You can have a direct measurement of the redshift, and that improves a lot the estimation of all cosmological parameters. So let's go to the topic which I was introducing at the beginning, the effective theory of dark energy. So this is a theoretical framework for defining a very general approach to the study of dark energy, particularly dark energy perturbation. So you write down an effective action, which is the most general one, which breaks time differences invariance, which is the symmetry which we expect to be broken by the fact that the universe is expanding. So there is an arrow of time. So the universe is not invariant under time translation. And so when you apply this to gravitational waves, you get this effective action. So you see that there is a possible, naturally predicted by this theory, difference between the speed of gravitational waves and the speed of electromagnetic waves. Not only that, this quantity can actually be time dependent, okay? So this justifies theoretically, basically, the phenomenological approach, which I was showing you at the beginning, where I was assuming some kind of redshift dependence. And on top of that, there is also this possible variation of the effective Planck mass. So these coefficients here comes from the coefficients of the Ricci scalar in the action, and this also then is propagated to the gravitational wave action, okay? So if you put all these results, so that implies that when we, making a connection with what I was showing you earlier, from the variation of the speed, you can constrain these M4 coefficients and effective Planck mass ratio. So basically, you're able to set constraint on the effective theory of dark energy using gravitational wave multi-messenger events. Then, if you write down the equation of the gravitational wave propagation coming from the effective action, you will see that it's given by this modified gravitational wave propagation equation, in which you see that the friction term is not just given by the standard Hubble parameter which you have in general relativity, but you have this extra dependency on the derivative of the speed and the derivative of the effective Planck mass. This omega quantity, basically, it's related to the effective Planck mass. And also you have different the coefficients of the Laplacian. So these are the effects that you expect in a modified gravity theory described by the effective theory of dark energy. So you can apply this, you can solve this equation. And once you solve this equation, you see that the ratio between the observed and emitted gravitational wave amplitude is not just given by the ratio of the scalar scale factor, which is what you expect in GR, because if you assume that the graviton is massless, basically it's the same as the redshift of a photon. But you have these extra effects, which are given by the ratio of the effective Planck mass and of the speed at the observer and at the emission. Okay, so if you then use this to make a prediction about what you actually observe, which is this quantity in the denominator of the observed gravitational wave, which is called gravitational wave luminosity distance, then you will see that you can find this general prediction based on the effective theory for the ratio. So for the distance ratio. So the distance ratio will be given by the ratio of the effective Planck mass at the source and at the emission, and also by another extra factor of the ratio between the speed at the source and emission. Okay. So then if you assume that the Planck mass is constant, you can do something similar to what I showed you at the beginning. I mean, you can actually derive some kind of consistency relationship, assuming a low redshift approximation. And this basically will tell you that if the Planck mass is constant and the only quantity responsible for the distance ratio deviation from the general relativity prediction of 1, then you will get that this quantity that I'm denoting with epsilon has to be 1. Okay, so basically, if the Planck mass is constant and the gravitational wave speed is not constant, then at low redshift, this relationship should be satisfied. So in fact, if you plug into that formula the observation of GW-17 at the 90% confidence level, you get that epsilon one is in fact within the bound, 90% confidence bound. So that means we don't have any evidence from that event, at least, but the Planck mass is not constant. Okay, and then let me go now start to talk about the final part of my talk. You can actually develop some even more interesting consistency relationship if you apply this effective field theory to some gravity theory. Specifically here, I will be talking about Ordenski theory, which are this theory which admit this second order equation of motions. And they differ from general relativity by having a much more complicated Lagrangian, including an extra scalar degree of freedom. So if you assume the Bredin parameter to be 0, for example, and you use the prediction of effective field theory for this theory, you will get this relationship, which I'm showing here, which is a multi-messenger consistency relationship. So on the left-hand side, you have non-gravitational waves observation, specifically large-scale structure. This eta parameter is related to the ratio of the two Bardian potentials. So it's it's called slip. It's one of the manifestation of the modification of gravity. And this G psi is the quantity which determines the structure formation. And this alpha b is a constant in this case, by assumption. And then on the right-hand side, you have the distance ratio and the speed ratio. So this tells you that for very large class of theory, which correspond to alpha b equal to constant, which also includes general relativity, this apparently independent set of observation, which are large-scale structure observation and gravitational waves observation, in fact, they should be related to each other. Okay, they cannot. If the universe, follow this kind of theory, then this quantity must be related. Okay, so these are very strong and important tests of modified gravity because they tell us how to compare different observations without assuming any model within the framework of this Ordenski theory. So let me give you some more detail about how this can be further generalized. So the quantity which I was defining earlier with G psi is the quantity appearing in the Fetty-Poisson equation. So this first is the equation which is responsible for the structure formation, and this third one is the one for lensing. Okay, and then the eta parameter is defined by this ratio. So in the case of general relativity, just to give you some practical idea, eta is equal to 1, alpha b is equal to 0, and the speed of gravity is equal to c. Then in that case, you would have that the consistency relationship will tell you that G psi, which is the Newton constant if you want, is given by the ratio of the distance, gravitational and electromagnetic distance. And in fact, if the universe is flat, that it will tell you basically that the Newton constant is not varying. Okay. But otherwise, this gives you a way to estimate a possible variation of the Newton constant from gravitational waves observation, specifically from the ratio of the two distances. And then you can actually find a more general consistency relationship without making this not simplifying assumption, but without making this assumption of constant braiding. And in that case, the math is a bit more complicated, but the main idea is that you can make a more general estimation of the effective gravitational coupling, which is the one which people measure in muscular structure observation. And in this case, it will also depend on alpha b, and then it will depend on other quantity which are related to gravitational waves observation. So basically, the main take-home message of this formula is that you can make a estimation of the effective gravitational constant or coupling using a mix of large-scale structure and gravitational waves observation. Okay, and the consistency relationship in this case tells you that the one that you estimate directly from gravitational waves observation and the one which you infer from gravitational waves observation, applying the theoretical framework I showed you earlier, they should be equal to 1. If they are not, that means that some of the assumptions which were used to derive this result are inconsistent. Either the universe is not following Ordenski theory, or the effective field theory is not correct, etc., etc. So these are basically strong tests of the consistency of these theoretical frameworks. Okay, and of course they are also satisfied by GR. So here I'm showing you an example of how you can test this consistency condition. So here the green line corresponds to the G effective you get from DAISY data, so large-scale structure data. And then the blue data point, this is GW-170817, so it's a single event. And then the red lines, these are dark siren constraints from the analysis that Sergio was mentioning. So as you can see, there is an overall consistency between all these constraints in the sense that there is no region when there is no overlap. So that means that the consistency conditions are in agreement with what we observe. Okay, so the universe seems to be consistent with Ordenski theory, if you want, and that also means that it's consistent with GR because GR is part of the theories. Okay, so then what the power of this multi-probe consistency condition is that you can combine together quantity from different apparently unrelated observations, like multi-messenger, for example, which constrain the speed of gravity. Then you can use large-scale structure for G effective and eta, and then you can use the luminosity distance, which are and the electromagnetic luminosity distance, which again are a multi-messenger observation. And then altogether they have to satisfy this consistency relationship. So I think there are 2 minutes left. I think I will not go through the conclusion, and I will just finish here.
Great, thank you, Antonio. So, is there any question from the audience, either Sergio or Antonio? Okay, I think we don't have any question at the moment. So thank you, Sergio and Antonio, again for your very, very nice presentations. So basically, we are almost finishing our seminar. And I just want to finish, mention that our next seminar is going to be June 18th. We're going to have 2 presentations from Fabian and from Leonardo. And also I want to mention or to remind you that if you are interested in to present in the seminar, please you can contact us, either Marcio, Claudia, Odilio, or myself. I think we have a question there, Alexander. Yeah, Alexander, go ahead.
Yes, thanks. I have 2 quickly questions. One for Sergio. Sergio, in the last slide, you show one plot. You can you can show us the slide.
Yeah, sure. Okay, so sorry. So you mean this one?
Yes. This constraints is a Gaussian processes?
No, this is using this piecewise cubic Hermite interpolating polynomial. So it's a different type of non-parametric reconstruction. In principle, Gaussian process could be something that be explored, but so far we have not done it.
But this process is model independent, like Gaussian process or machine learning. I don't know.
Okay, this is model independent in the sense that the cubic spline is based on interpolation. So basically, it's an interpolation using these cubic splines, and but we have two parameters which are controlling some of the conditions that we need to impose in this case, which are the monotonicity of the method, of the distance ratio. But more than that, everything is model agnostic. Like we only need some constraints for computational reasons.
Why agnostic?
Sorry?
Why agnostic?
So
This
it's
very
agnostic in the sense, sorry?
yes.
Yeah, so in
This-
the sense that this is an interpolating polynomial. So that's why it's agnostic. There are some constraints on the distance ratio, which I mentioned, but these are for computational reasons and
Okay.
not physically motivated.
Okay, thanks. Very interesting. And the other question for Antonio, please.
What do you mean?
Stop share.
Oh, only which specifically cosmological tests is a large-scale structure? Is BAO or which specific test, you know?
Yeah. So that theoretical relationship is completely general. So you can use whatever cosmological probe you wish. Okay. So practically speaking, I have applied it to I think this is the use BAO, yeah, to constrain the effective gravitational coupling. Yeah. But a priori, that's that's just the quantity appearing in the effective Poisson equation. So it's a fundamental equation. So when you apply it to predict different observable, it is still valid. So you can apply to anything you want.
Okay, my question is why you have, for example, data points from BAO in terms of distant luminosity or distant horizon. I don't know. It's only that, but very interesting work. Nice presentation, both speakers.
Yeah. Okay, but so basically, they use BAO to estimate the gravitational constant running in DESI. Yeah.
Yeah, it's possible apply the same method that Sergio mentioned in his presentation.
You see, what I showed you is a general mathematical relationship. Then you can use whatever parameterization you want. So basically, I should have emphasized on this. So these are theoretical model-independent relationship, okay? Because they're valid for very large class of theory. For example, if you know braiding includes a lot of modified gravity theory, and the one I showed you at the end is all of density theory. So then what you can do is you can plug inside this relationship the results of the analysis that you have performed, assuming whatever parameterization you wanted. So yes, you could use p-chips, you could use alpha-chi-naught, you could use whatever. Basically, those are fundamental physics relationship, and they can be used to test the results of the analysis, which is obtained using any parameterization. There is no parameterization assumption anywhere.
I understand perfectly. Thanks, Antonio. Very good job. And we are in the same wave. I need to speak about that. Thanks.
Okay. So to summarize it, basically the speed of gravity and the gravitational constant are actually not independent quantity. They have to satisfy somehow some kind of constraint in a self-consistent model of the universe, which satisfy, this kind of theories.
Very interesting.
Thank you. Thank you very much. Thank you to the speakers for these fantastic presentations, and thank you all for your attendance. So please let us know if you're interested in give a presentation. We have available dates. Please let us know. So if no more questions, I think this is the end of our seminar for today. Thank you very much. The space is here if you have any question or comment.
Bye-bye.
Thank you. Bye.
Okay, thank you. Bye-bye. Thank you.